Hello everyone, hope you are doing well. Today I gonna talk about critical flow. This is chapter 10 in our textbook, and in today's lecture I only provide an introduction to the chapter. In this introduction I will define Froude number as one of the most important dimensionless quantities in hydraulics engineering. This is a number that we use to classify flow in open channels in different classes based upon the velocity of flow. You remember that in previous sessions we used different factors, parameters to classify flows in different classes. For example, we defined uniform flow and non-uniform flow based on the variation of flow parameters in space, or we defined steady and unsteady flow based on the variation of flow characteristics by time. Now we will consider flow velocity. We will define a new parameter. This is third number. Then with respect to the value of third number in our channel flow or in our flows, we will define new classes for open channel flow. Let's see what is the third number. Third number, as you see here, is a dimensionless quantity which represents the ratio of average of flow velocity to the ratio of the wave celerity. This is wave celerity, or the speed of the crest of a wave in channel. I will talk a bit more about wave celerity in the next slide. It can be also interpreted as the ratio of inertial force. You see the U inertial force represents inertial force. You know F equals to ma, and it's proportional with the rho v squared. And here we have acceleration due to gravity g. Therefore, the denominator can be considered as a gravity force. And consequently, third number can be interpreted as the ratio of inertial force to the gravity force. Based upon the value of third number in different channels, we will divide flow in three different conditions or three different regimes. For the cases that Froude is less than 1, it says that U is less than, celerity is less than this value. Therefore, we say it is subcritical flow or tranquil flow. For the case that we have higher velocities in our channels, like in the figure in right, U will be greater than celerity, therefore third number will be more than 1, and we say the flow regime is supercritical. Your book compares the terminology of supercritical and subcritical with that of we use when we compare the velocity of an airplane with the velocity of sound. As you know, similar to airplane with supersonic and subsonic speed classification, here in open channel flow, we will have supercritical and subcritical classifications. And to classify flow, as I told, we need third number. And when we talk about third number, we have two important parameters. One, velocity of or average velocity of flow, and this term, which is wave velocity or wave speed, which is called celerity. You see, celerity is the speed of the crest of the wave in a shallow water. If it is a wave which is created through the motion of this plate here, it can move downward with average velocity of flow and also the velocity of the crest of the wave, which is called celerity. Here I prepared the short movie. Let's see, and I will talk about the celerity and how we can see celerity in a flow. In this short movie, we see how waves are generated in a wave flow. This is a paddle moves with a single frequency, and you see that some waves created here, and it takes a few seconds for the waves to move down to the flow. And speed of each of these groups of waves moving down to the flumes is called as a group velocity. If you fix your eye on the crest of one of the waves and look how quickly this wave is moving, the speed of crest of the wave is referred to as the wave celerity. Actually, the wave celerity is therefore the speed of top of the wave, and in deep waters the group velocity is only half of the wave celerity. Here we see some examples that can help us to get more insights about the wave celerity and definition of different classes in the flow. In previous movie, you saw that I used a moving paddle in order to create a wave at the upstream of our flume. But to create a wave, we can easily drop a pebble into the water, and then we can check how the created waves moves downward or upward. And you will see that based on the different classes of the flow or based on different value of Froude number, uh, wave propagation will vary. Let's start with a case that we have still water, or we assume there is no motion in the channel, no water motion in our flow. And this is a pebble dropped into the channel. What will be happen? The waves will start to create and move all around the pebble. And we know that the uh, celerity of the wave is c, therefore there is no resistance in terms of motion of the flow within the channel. Therefore, these waves can easily propagate at any side with the average velocity of c equals to the celerity of the wave. In another case, this is a pebble dropped into the water, which it has a flow with the velocity of critical velocity. Let's say critical velocity because the example says this is critical flow. And critical flow is the condition that velocity of flow exactly equals to the celerity exactly equals to the speed of the wave. Therefore, what will be happen? Wave just after being created moves downward with the average velocity of the 2c, which equals to summation of c plus v. And as we said that v equals to c, therefore average wave velocity moving downward will be equal to 2c. The other case is the subcritical flow condition, which means that Froude number is less than 1. Therefore, uh, considering the Froude equation, let's see again here, this is our Froude equation. Froude equals to u or v or the average velocity divided by celerity. When we say that Froude is less than 1, it means that u is less than celerity. Therefore, and let's have this equation here. Therefore, we can say that when the wave would like to travel each side, especially at travel to upstream, it can move upstream because c is greater than v, or we said that this is Froude number. This is supercritical condition. Subcritical condition. Froude is less than 1, therefore v is less than c, or c is greater than v. Therefore, wave can propagate upward. And also, because wave itself want to go downward, and flow is also to the downward, therefore, with higher celerity or higher average velocity of the waves, uh, equal to v plus c, waves will move downward also. Therefore, we can say that in subcritical flow, any created wave can move both upward and downward. And in the last example, we assess the supercritical flow condition. If this is my Froude number, supercritical means that Froude is greater than 1. Therefore, velocity or average flow velocity is greater than the celerity. In other words, the velocity of blue flow is higher than the velocity of or speed of the waves, which is in red. Therefore, just uh, just after the creation of waves, as v is greater than c, the wave cannot propagate upward, and it can only propagate downward with the velocity of with the average speed of c plus v, which shows the supercritical condition. Therefore, if in nature, if you drop a pebble into the water and so that the wave or created wave only moves downward, you can say that the flow regime is supercritical, and it means that our velocity is higher, flow velocity is higher than the celerity. Here we can summarize all the information we talked so far. If Froude number equals to 1, we can say that the flow regime is critical. 1 Froude equals to 1 can be showed in this way. Flow velocity equals to celerity. For the case that Froude is greater than 1, the flow regime is supercritical, and for the case that Froude number less than 1, the flow regime is called subcritical. Here I asked again about the root GD. What it's imply? Actually, it's nothing than the speed of the crest of wave created in a shallow water. How we calculate this speed, or where is the origin of this formulation, we will talk in the other sessions. And in this slide, I am going to explain flow depths with respect to the different flow regime. Okay, uh, before comparison of flow depths, it is necessary to talk or to define new terminologies about the depths of flow. You know that when the uh, water depths in a canal which has uniform flow, we say this is normal depths, and we showed normal depths with U0. But when we talk about critical flow or subcritical flow, also we compare the flow velocity and celerity. We can compare the depths of the uh, flow with respect to the critical or supercritical or subcritical condition in the flow. Okay, when flow velocity v equals to celerity, let's this is a critical condition, and in that condition, flow depth is called. Let's show the flow depth with yc, or from here we will say yc is critical depth. We can say in this form also critical depth is a depth in which flow velocity equals to the wave celerity. If your y, or the depth of flow in your canal, is greater than yc, like this case, yes, you see that now this is yc, this is depth of flow, or y0, normal depth in my canal, and I see that y0 is greater than yc. What will be happen? You see that for that case, we say that flow condition is subcritical. And also, by contrast, when the y is less than yc, this is our condition, y0 is less than yc, therefore flow is supercritical. We will say this is supercritical condition, and as you see here, for the case that y0, as I told, equals to, or water depth in the canal is just equal to the critical velocity, this is called critical depth, and therefore we have critical flow condition, or our flow regime is critical in the channel. Now it can be asked that why in this case that y0 is greater than yc, we say subcritical. Actually, we should come back to the concept of the continuity equation. We know that by increasing the depth of water in flume, by increasing the depth, what will be happen to have a constant discharge? Velocity will must be decreased, because a times v equals constant, and when you increase y velocity, or increase let's say increase the flow area, to have a constant discharge, flow velocity should be decreased. And when the flow velocity decreases, it is assumed that velocity of flow is less than critical velocity. And never forget that critical velocity is just celerity equals to root GD. Therefore, the condition is V less than Vc. What will be happen? If V less than Vc, Froude will be less than 1. And this is subcritical flow condition as we talked in this slide. Therefore, for the case that V is less than Vc, you see that Y can be or Y would be greater than critical depths, and the flow regime is subcritical. The same condition is here. When the Y is less than critical velocity, when the depth of flow or Y0 is below the critical depths, we have definitely higher value of the velocities than celerity. Therefore, V would be greater than celerity. And for the case that V is greater than velocity, we have definitely a rapid flow condition, which is also called supercritical flow. Yes, actually a rapid flow, or sometimes you can hear tranquil flow, rapid flow. These are general terms, but in engineering, we say supercritical for rapid flow and subcritical for the tranquil flow. And the critical flow or critical velocity just is the velocity of flow equals to the celerity. And in that cases, flow depths will be equal to the critical depths. The other characteristic of a channel is channel slope. Yes, channel slope. And with respect to the slope of the channel, we can say or we can get conclusion about the flow regime. We have here three different slopes. The first one is mild slope, the second one is steep slope, and the last one is critical slope. When we have a mild slope, as you see here, what kind of flow we had? We had subcritical flow. Therefore, we can say that when the slope is less than critical slope, we will have a mild slope channel, and therefore flow regime would be subcritical. The slope of the channel is less than critical slope. Therefore, it can be concluded that for any channel for a given discharge, one slope is called critical slope. What do you think? Which slope is critical slope? Hmm? Yes, the slope in which flow can move downward identical to the celerity is called uh, critical slope. Therefore, if your slope, for example, let's see this example, if the slope of channel is higher than critical slope, what will be happen? Flow would like to move very fast, yes, even faster than the critical velocity, even faster than the wave speed, yes. Therefore, we will have supercritical condition. And for the case that slope just equals to the channel slope just equals to the critical slope, what will be happen? Flow velocity would be equal to the celerity, equal to the wave speed, which can be created in this channel, and we will have a critical flow regime in such cases. Therefore, I can summarize in these are about the calculations. Let me summarize this lecture here, and we can talk about the computations of flow in critical condition in next lecture. Uh, we said that if um, flow velocity is bigger than celerity, Froude number will be more than 1, and therefore this is supercritical flow condition. When we have a supercritical flow, it means that the velocity is bigger than celerity, or water depth is less than critical depth. By contrast, when the Froude number is less than 1, flow velocity is less than uh, critical velocity, and therefore the condition is a subcritical flow. And for the case that flow velocity uh, exactly equals to the celerity, depth of flow in the channel would be equal to YC, and this is called critical flow condition. Okay, that's all for this lecture. See you in next lecture.